Good day. My name is Shalom Mandeville. I'm the executive producer of Science is Your World. And for the first time since the show first started in 1988, we're doing an on-location shoot, and I hope you enjoy this. And I'm very proud to present to you my guest today is Dr. Howie Donahoe. Dr. Donahoe is a geologist with the Department of Natural Resources, and he's also a visiting professor at Dalhousie University. And I'll hand this mic over to Dr. Donahoe, and he can explain what this is all about.
Thank you, Shalom. This is a walk about granite and about the rocks at Peggy's Cove and about something of our heritage here in Nova Scotia, about how the cliffs, the ironbound coasts, and this beautiful rocky series of inlets have all been formed. So we're going to take about an hour's walk, starting here at DeGarth Memorial Provincial Park and walking out towards the sea, towards the beautiful Peggy's Cove Lighthouse, and look at all of the landforms and the way that they formed, and look at some 450 million years of Earth history. So we start with granite as a building stone. We start with this beautiful sculpture that William DeGarth created behind me. And what this is all about is about granite. It's about sculptures and how long they last. It's about building stones and how long they last. And granite as a rock, granite as sort of an icon about all of the things that are durable and longevity. So this is one rock that doesn't have very much soil. So what we're going to do is start here, walk down to Peggy's Cove itself, and look at all of the different aspects of the cove, how it came about, then go on to the lighthouse and talk about the rocks themselves and how they got here. We're here at the next stop, which is right on Peggy's Cove itself. And this beautiful cove is the site of so many photographs, you'd think it was almost photographed to death. And painted on and on and on. But it is so beautiful. It represents, in many ways, Atlantic Canada. And of course, there's two very interesting questions to ask about this. How did it get its name, and why is the cove here? I'm going to ask Jennifer this very question. Jennifer, how did the cove get its name?
Well, actually, Peggy's Cove has a lot of history, and its name is one of those areas that is included in that. The first is actually a more colorful of the two. It actually is legend that Margaret was a lone survivor of a schooner crash off Halibut Rock. She swam ashore to Peggy's Cove, and she was known as Peggy of the Cove. The second origin of the name Peggy's Cove is actually a little less creative. Basically, they figured that it's a shortened version of St. Margaret's Bay, and that's because Peggy's Cove is located just off the mouth of St. Margaret's Bay.
Why the cove is here is kind of interesting because it's not simple. It's a history of glaciation and many, many millions, hundreds of millions of years before that as to why the cove actually was produced here. So the question starts, how did the cove form? Some 380 million years ago. Now we'll explain just what happened then, but all I want to tell you briefly at this point is that the cove started right off to my left, your front, as a result of fractures and cracks that are zones of weakness that were produced by two large plates colliding together 380 million years ago. And it's this aftermath, sort of the calling cards of this huge collision, that produced the cracks and fractures that led to something that was easy to erode by the glaciers and by running water. So I have a series of pictures here to describe just what happens. After the collision of two continents, and we'll talk more about those continents, there were zones of weakness that were vertical, as you see, as well as horizontal. Now, we've only shown a cross-section. It's like taking a cake and cutting down through it. So we've only shown one plane or one direction through the rock. If we were to go the other way at right angles to it, there'd be the same type of shape of fractures and zones of weakness. So what has happened that before glaciation, which is some 100,000 years ago or thereabouts, there were zones of weakness. What has happened is that during glaciation, the glacier has exploited these zones of weakness to create changes in the shape of the land. So what is happening is that under the zones of weakness, there and there, there's smaller cracks smaller pieces of rock, and the glacier can actually put its icy hands around those rocks and pluck them out. And the way that it does is like this. The ice actually goes in, goes around in the cracks because it's under that pressure of maybe 2 kilometers above us, as much as that much, 2 kilometers of ice. There's almost a liquid at certain points as it flows, so it goes into the cracks and then it freezes again, and as it freezes it recombines with the 2 kilometers of mass and actually pulls out that chunk. So that's actually how we wear away the land. So when we finish all of that, here's what it looks like. Peggy's Cove is a depression then that is eroded away preferentially by the glacier, plucking action, takes one after another out, and the same with the ocean side over here past the lighthouse, the same type of thing. So we get holes where there's more cracks and fractures, high ground where there's fewer, and then more holes or more lower areas where there's more cracks. So that's how you erode away a cove like Peggy's. So that's how we've gotten the name. That's how we've actually gotten the cove right here. Because after the glaciers melted, all the water in the sea rose again, because it had to be taken out to create the glaciers, and then it was put back in as they were melted. So that's why there's water here now. And a little bit earlier this evening you were talking about the bottom of the sea. Well, actually at one time, because the weight of the glaciers was so much, this was the bottom of the sea, because the land was depressed by the weight of the glaciers. As they melted, sea level came up faster than the land rebounded from the weight, but slowly the land went up faster than the water after a while. So that's why this is dry and that's wet. But at one time this was mostly wet. So from here we go on to talk about the actual rock, the granite itself, what's in it, what constitutes granite, and why it's so interesting, and what its history is. So here's where we go back 400 million years or so. We're here near the lighthouse, and this stop is all about what is a granite, you know, where it came from. So we're going to explore what the name granite means to geologists, what are the minerals that are in granite, how we know something about granite, and then the whole story of how it got here, how this particular granite right at Peggy's Cove actually was formed and moved to where it is now, and how it was uncovered so that we see it and walk on it today. Claire, was this granite that we're standing on now always a hard, solid rock?
Well, it used to be molten rock, and like lava that you see, and it hardened below the surface of the earth, as opposed to like in volcanoes where you see them exploding on the surface of the earth. This cooled and crystallized below the surface of the earth, and through erosion and uplift was brought closer to the surface and is now exposed, so it wasn't always exposed.
And I'm going to ask Jennifer to talk about some of these things. These are little blocks of rock that are stuck in the granite.
Okay, if you want to walk over here, you can actually see there's actually a change in the rock. Right here you can tell this is not the same type of rock as the granite which surrounds it. Okay, this actually gives some kind of indication to what kind of rock was here before the granite. And so you can see a number of them around if you look. They appear slightly like a gray color, a slightly different color, and in some of them you can actually see layering. Okay, this layering indicates that the rock was a sedimentary rock, which means that it was a rock which was made up of worn pieces of another rock and deposited. So here's a xenolith. You can't see any structures in it, but if you want to look around, here's actually one. You can see the layering of the rock. Okay, and that indicates that it was a sedimentary rock, which means it formed from the wearing away of other rocks. So what we're going to do is we're going to take a little walk and get out of the wind a little bit, and we're going to go over the history of this area over the last 450 million years.
This is the long-awaited answer, or question, I suppose. Where did granite come from, and how did this granite get here where it is now? So what we're going to use is a series of little diagrams like this to show you exactly what we think, what geologists think came about. So now you know from what Claire said what a granite is, and from what Jennifer talked about, that there's something that's in the granite here that gives us a clue as to where it came from. There's chunks that are not part of the granite that were picked up by the granite and brought upward. Some are layered, some aren't. We want to talk about those layered ones because those are the key. And if you go out of the granite towards Halifax or far to the north, then you'll come across layered rocks. And these were there first, before the granite came in. So some 600 million years ago, the Earth was much like this where we are now. It was one continuous large plate of the Earth's crust. And for reasons that we're not certain we understand as geologists, there's sometimes high heat flow. And this high heat flow began to break the crust of the Earth, the heavy black lines, because it was actually pushing it up. And it's just like a chocolate bar. When you begin to bend it, it breaks and snaps. Well, that's exactly what happens here. We begin to form a little valley. And if the valley continues, it gets deeper, very deep, sometimes even volcanoes in the center. And if it continues, then it fills in with seawater because it gets so low, so deep that the sea floods in. So now we begin to form a small ocean, a mini ocean. And if this continues, the heat continues to move up, then the two different plates, two different continents begin to move apart. And that's what we had happening here. So this waltz of plates, and let me define what the plates are. Here on your right is Antarctica, South America, Africa, Australia, India, something we called Gondwana. Over here on your left is a group of continents that includes what is now parts of Scandinavia, the British Isles, Canada, most of the U.S. and Canada, some of Mexico, excluding everything from about Reno westward and Kamloops westward. All of that had not been added to North America. So everything except those guys in North America were part of this side. So this continues to open up. We have a big ocean, and there's rain, and there's rivers that flow down, bringing mud and sand to the ocean floor. And in detail, here's the African side, the Gondwana side. And this layer of red and green that I've shown in the diagram is a series of muds and sands that deposit off the coast of this ancient Africa or South America. We're not exactly certain, but it's between the two where they came together. And as they build up here, sometimes there's earthquakes, sometimes there's just the buildup of sand and mud, and it becomes very unstable, or it gets shaken by an earthquake and it tumbles down into the deep sea. So all those rocks around Halifax, Bedford, and that area all arose from the erosion of mountains, the deposit of sand and mud, and then the collapse of the sand and mud and going down into the deep ocean to form these thick layers that are actually quite thick, sometimes as much as, well, as much as Shalom is high, 2, 3, 4 meters as the very largest, most of the time just our height. So these represent continuous earthquakes or continuous collapse of this huge amount of mud and sand. For reasons, again, that we don't understand, then this heat engine that keeps driving the continents apart ceases and begins somewhere else. So now the continents begin to move back towards each other. North America, Gondwana land, or Africa. And the resulting collision between continent and continent produces a mess like that. And that mess is the creation of a huge amount of rock coming together, sliding up on top of one another. In order to get high mountains, it's just like ice cubes. In order to get a large amount of ice above water, you have to have more than 7/10 of it underneath the water in order to hold up what's above. Mountains are just the same. So if this is sea level, then even I've exaggerated this too much. I should have increased this depth considerably. And as you cut down the mountains by erosion into relatively flat lands like we have now, then we have the roots of the mountains and the roots of these granite intrusions. So that's why Claire and Jennifer were talking about uplift, erosion, glaciation to this level right here. And that's why we have the granites at this level, cutting right across. That also explains now the complicated 400 million year history to why we actually get granites generating in the very first place. So you can see it's very long, very involved, and very complicated. And I've made short work of it in just 10 minutes describing it because, my goodness, it's taken us as geologists some 30 or 40 years to understand what I've said in 10 minutes. Come on down this way a little bit further, we'll examine how the rock got sculpted. The sculpturing of all of this is very interesting. Marie-Louise, would you and Claire stand in some of the grooves here? These little grooves right here. Stand right on this one right here. Marie-Louise is standing on a groove that runs down this way, and Claire is walking up a hill over here on this side. This becomes steeper up here and that way. Where Marie-Louise is, that's just a small little groove that runs up. These are all created by the glacier moving over top of this land with big chunks of rock in tow right at the base. So 2 kilometers or so, lots of pressure, big rock at the base, moving it along. Where Claire is, maybe it's not clear whether it's bigger or whether it's just easier to break out. But this is a plucking action in here that took out parts of this sheeted intrusion, this aplite, and then created this little groove right through here, a bigger groove. I shouldn't say little. Then as you look around, you'll see all sorts of little grooves and bigger grooves. Now, none of these by themselves will tell us which way the glacier came from. So we have to look for something more. And this something more is the shape of the land. The shape of the land runs from shallow dip to steep. Shallow, steep. Shallow over the hill to the ocean and steep. And this series of shallow, steep gives us the indication of the direction of ice flow. So the movement is from the shallow side to the steep side. So now we can interpret these grooves to say the ice moved this way and the actual direction is from northwest or northerly to southerly, like that. And that's how we do it. That's the actual show that we use. One of the interesting questions I had just a moment ago is, how can ice move uphill? I mean, we've been speaking locally about it moving up maybe as much as 10 meters and then going down again. Well, remember that 10 meters is insignificant compared to 2 kilometers or even a kilometer above. And the other thing is, just like water, water can go up and down and still flow as long as the source that it comes into is higher than where it goes out. And as long as you start the siphon effect, then it will go up and down and even higher locally than the source as long as the empty part, or where it's emptying out, is lower. So we're here at the last stop, and here I want to talk about why we look at granite. Well, you've heard granite is durable. Granite has an interesting history. As a takeoff on durability, people have used granite to represent a certain sense of themselves, a certain, I suppose you'd say, statement of their personal wealth, how long they're going to be here on Earth. Degarth left a lasting memorial to the people of Peggy's Cove and to himself, because he knows, as well as anybody who walks in granite, that it's hard. It'll last. Likewise, with so many other applications, the way in which we use granite for use in buildings. People build buildings which are very expensive because it's so hard to cut and to shape out of granite to make a statement about their personal wealth. But there's another source of wealth in granite, and this wealth is something that Claire is holding right here. Marie-Louise, would you rattle those about? Rattle, rattle. These things that she's rattling are nothing more than a so-called tin can And this stuff right here. This is a black concentrate that I'm holding up right here. This is the ore of tin that has been taken out of a rock in East Kemptville, Nova Scotia, before the mine closed there. And it's tin ore. Tin was formed in granite, similar to this, and it's a very valuable metal. We use it all the time. And the other part of this, right here, this is just a tin can that was used for my cat. Rhiannon's cat food was kept wholesome because of a tin lining inside here. So when Marie Louise rattled around in here, the tin can is the application, and the black stuff right there that's fairly heavy is the tin ore. Marie Louise, just take that around and show everybody. So now we have more than just durability, statement of personal wealth, and sense of oneself. There's granite here, like this granite, that actually holds mineral wealth. And we geologists search for that because the demand from all of us creates a need for the use of minerals like tin. So we search for tin, and sometimes we're lucky we find deposits of it that can be, if all goes well, opened into a mine, like East Kemptville. And then one last thing, my other helper here has this beautiful slab of rock. Can you bring that over to me? Beautiful. Now this is a beautiful slab of salmon-colored granite, pale salmon, that's polished a little bit. Not as high a sheen as some rocks, but this is part of the durability of the granite building stone that's so often used. And not just building stone, too. Memorials in cemeteries. Same thing. It lasts. Countertops, yes. But you know, that wasn't possible when we renovated the kitchen 10 years ago. There was no such thing in Nova Scotia. And it was only over the last 10 years that people started using marble and granite, and suppliers will cut it for you as you need it. So in this tour tonight, we've talked about granite, what it is, how it got here, why we as people use it and depend on some of the mineral wealth that comes from granite. And also this is part of a larger program, because this originated at DeGarth Memorial Park. This is part of a larger program of Parks Are for People. So I thank you very much for coming along. Pleasure to have you here at Peggy's Cove. I have with me one of the people that was in the walk tonight. This is Marie Louise. Marie Louise, what is this rock right here? Is it granite?
Granite.
Yes. And do you like granite?
Yes.
Is that one of your favorite rocks?
Yes and no.
Yes and no. What's your favorite rock? Do you have a favorite? Do you like quartz crystals and things like that? And
I like quartz crystals.
yeah. Well, there's big quartz crystals in here, and we were looking at some of these earlier. And unfortunately, here at Peggy's Cove, the crystals, although they get up to as big as a centimeter or so, you can't take them out, and they don't have the beautiful shapes that you find in cavities. But I think Marie Louise would still be happy. Here, you can have that piece right there. Yes?